All right, so I think there is some internet problem. Okay, so we will restart it. Okay, so hopefully we don't have any problem during the exam. All right, so are you all there? Okay, cool. Okay, let me share the screen again. Okay, so welcome back. All right, so so as I said, so you can form a longer chain using a C2 unit of alkyne to generate Ni and react with first primary alkyl halide. And okay, so if you have a heavier alkyne, let's say you have a terminal alkyne, you have one substituent R, and you can also react with sodium amide. Now you form a Ni again, and will react with primary alkyl halide again. So then you form an internal alkyne. Okay, so it's very interesting. You can start from a C2 unit. You install one side of substituents by react with primary alkyl halide. Then you can use the product as the starting material for a second round. All right, the second deprotonation and the second reaction with primary alkyl halide. So from C2, you can have both of the alkyne side substituted using these kind of nucleophilic substitution with primary alkyl halide. Okay, so but you have to know the limit of this reaction. So the limitation of this reaction is that you cannot react with secondary or tertiary alkyl halide. All right, so you cannot say, okay, let's deprotonate this, and then we substitute this bromide here to form this. No, okay, so just keep this in mind. Be crystal clear that this reaction won't happen if you use a secondary or tertiary alkyl halide. So why? Okay, so sodium acetylide, okay, it can react with as a nucleophile. Okay, do the substitution reaction with primary alkyl halide. Okay, this is no. All right, but it can also act as a base. Okay, it can deprotonate other things or do an elimination reaction, which we will learn in the second half of this semester. So when it reacts with the secondary alkyl bromide, so the acetylide will deprotonate this H, okay? And then this bond broke, form a pi bond here, and this bromide leaves. So form it's a elimination reaction, okay? Why does that mean? Because this one become 2, all right? HBr and the alkene. Okay, so although elimination is not covered in the first half of this semester, but you need to keep in mind and you need to memorize that the alkyne, the substitution reaction won't happen if you use a secondary or tertiary. So if you see some of those target molecule I provide you and ask you to synthesize during the midterm 1, you cannot say, okay, can I build this bond using a alkyne substitution? No, you can't, okay, because this reaction won't happen if you use the secondary or tertiary alkyl halide. Okay, so to summarize this alkylation reactions, so you need to understand and can react with the primary alkyl halide to make a new CC bond. Okay, it's a very general route to large and more complex alkynes. And as you know, alkyne can be transferred to a lot of other functional groups. Like it can be reduced to alkene, and you can react with the bromide, HBr, or dihalogen, right? But so it's very useful reaction. But you need to remember that it can react as a base with secondary, tertiary alkyl halide. Thus, the substitution reaction to make a CC bond won't happen if you use secondary or tertiary alkyl halide. All right, so this is the final part of the first half of this semester, which is give you an introduction to organic synthesis. All right, so in principle, organic synthesis creates molecules by design, and synthesis can produce new molecules, and all those reactions you have learned are important tools. Okay, and especially those who making new CC bond, like we just talked about, the acetylide anion CC bond formation. All right, and this is a very good way we can build up the carbon framework of a molecule. All right, so so in order to propose the synthesis, so if I give you a target molecule, ask you to synthesize that, you need to keep in mind these important points. First, so you need to know what is the starting material, so what you are given, all right? So, what reaction to begin with. So if you choose to use this reaction, then what does it need, okay, as starting material? And let's compare it to what you are given, all right, and see, okay, that's the correct starting material. And then you need to understand all the reactions you have learned about what the reactions lead to, all right? What's the product of this reaction? And how the reactions are accomplished, like what regions and conditions you need to use. So you cannot just say, oh, I know this reaction leads to that, but I don't know how it works. No, you can't. Okay, you need to write down the conditions and all the regions you need to use to get everything right. Okay, and then you also need to know what the reaction limitations are. So what does that mean? So you know that, so you might vaguely remember that the alkyne can be used to deprotonation and nucleophilic substitution, right? To form a new CC bond. But you need to know it doesn't work with secondary or tertiary alkyl halide. Okay, so you cannot propose that. All right, and a synthesis, simply put, is to combine all those reactions you learn, and eventually you want to get the major product as your target molecule. Okay, so you cannot say, okay, this reaction, I propose this, but there is only 10% of yield for the first step. All right, and then in second reaction, this can be formed maybe in 5% yield. So this is not okay. Okay, so when you are required to synthesize a molecule, you are required to synthesize that as a major product. Okay, every intermediate you propose needs to be the major product of the reaction you propose. Okay, so strategies for organic synthesis. So I know this is quite boring, but we will give you some examples, so that's interesting. All right, so the first step, you need to compare the target molecule and the starting material. So first is find similarities. So most of the problems you encounter during classes are not that difficult. So we are not trying to challenge you or something to see if you are smart or something. So we are just trying to know whether you know the basic reactions and how the reaction work. Okay, so then you need to consider reactions that produce the target molecule as a major product. So what reaction could have you used to make the product that is listed on the exam or in reality? Okay, and then so a way of designing a synthesis is called a retrosynthetic analysis. So this process is like working backwards. So you got what you want to synthesize, and then push backwards one step. Okay, what does it come from? Okay, then one more step, and see whether you can push several steps and to the starting material, and see, okay, we got this. All right. So it's like a retrosynthetic like point of view. Okay, let's just jump to the example. So if I ask you to synthesize octane from one pentyne, all right, from left to right, what are you gonna do? All right, so I'm not challenging you for this, so I'm going to show you how to do that. So the first, you look at the target molecule. Okay, it's octane, right? It has 1, 2, 3, 4, 5, 6, 7, 8 carbons. How about starting material? 1, 2, 3, 4, 5 carbons. All right, so we are missing 3 carbons, right? So we somehow, eventually, we need to put 3 more carbons to the starting material. Okay, then we think about it retrosynthetically. What does that mean? Okay, how can we make the product? How can the product be from? Okay, so what can lead to the product? So we know that octane is an alkane. Okay, it can come from the reduction of alkene or alkyne. So you can use the alkyne to hydrogenate it. Hydrogen, palladium, carbon. It cannot stop at alkene, right? Remember? And then you can directly get octane. You can also start from alkene, double bond here. Or you can hydrogenate that and to give octane. Okay, so that's the first step. You think about it retrosynthetically. Okay, then you compare the starting material and the intermediate Okay, at first you compare these two. Now you compare these two. Okay, so we have a way to make this from these two. How can we start from this one? Okay, and then this is 5 carbon. This is still 8 carbon. We need to add 3 carbons. So it's quite simple because the only way you have learned in the first half of the semester to make a new CC bond to add more carbons to the carbon chain is the satellite calculation. So there is no other choices. Okay, so we won't test you with something you haven't learned yet. But I have to warn you that this will get exponentially difficult as you proceed in the organic synthesis. So for example, if you have in the second half of the semester, you may have learned 3 or 4 more ways to synthesize a new carbon-carbon bond. So it gets complicated, right? But up to now, you only know one way to construct a CC bond, all right? So this way, it's a calculation of a satellite, all right? So 5 plus 3, right? You can start from 1, 2, 3, 4, 5. And you do the calculation, use alkyl bromide, 1, 2, 3. You got this, okay? So that means we are very close to the starting material, right? So the alkyne as a precursor is more advantageous because you can form a new CC bond. If you use alkene, there is no way. There is ways, but there is no way you have learned so far to construct a combination of 5 carbon and 3 carbon. So apparently this is the good way to synthesize it. Okay, then again, we compare it with the starting material. It's just a deprotonation, all right? So you have 1, 2, 3, 4, 5, and deprotonated, become nucleophile, all right? So after you do all the analysis, you need to give me a forward synthesis, all right? Completed synthesis. So start from 1 pentyne, you deprotonate it with sodium amide to form a nucleophile and react with 1 bromopropane to form a new CC bond here. And then you hydrogenate it, use a palladium non-carbon. It cannot stop at the double bond. It will get fully reduced to form the octane. So you need to check the forward synthesis to make sure every starting material, every intermediate are correct. And the conditions you use are correct, all right? So a correct retro analysis does not guarantee that your forward synthesis is correct. So what does that mean? So you may make mistakes, okay? So, and you may forgot to write the conditions, you may forgot to add this region, that region, okay? So in midterm, so when I ask you to devise a synthetic route, I'm not asking you to do a retrosynthetic analysis, okay? You cannot just give me an analysis. You need to, so you can do the analysis on your draft paper, okay? The paper you won't submit for the exam. But eventually what can be accepted as your answer is only this, the completed synthesis with all the starting material, intermediates, and the regions conditions listed, okay? That is counted as a completed synthesis. All right, so I'm going to give you several more examples. All right, so for example, if I ask you to synthesize 1 pentyne to, no, I'm asking you to synthesize cis to hexane from 1 pentyne. So what I'm going to do? So I'm going to give you 2 minutes to think about this and I will show you the answer. All right, 2 minutes. You don't need to write a complete synthesis right now. Just think about it, how you can synthesize it, because this is quite similar to the problem 1, right? So in 2 minutes, I will show you it, okay? One pentyne to cis-2-hexane, 2 minutes. All right. All right, I think most of you should get it, right? Okay, so let's see. Okay, the alkene. How can you get alkene? And you need to be aware, although I'm not drawing it, this is cis alkene. So to get cis alkene, so you can do it from alkyne, right? So this is how many carbon? 1, 2, 3, 4, 5, 6. All right, and this is 1, 2, 3, 4, 5. Okay, so that means that we need to add more carbon, add 1 carbon here, and okay, then we consider, okay, this is cis alkene. It can be formed from alkyne, right? So we have 1, 2, 3, 4, 5, 6. Okay, alkyne. And do you remember what's the condition? Because from alkyne to alkene, the hydrogenation which only stop at alkene is called the catalyst is called a Lindlar catalyst. Hope you remember. This can stop at alkene, and it is the trans reduction, which is a syn addition of the H2 to alkyne. Okay. And then if you compare this starting material and this intermediate, right? This is 5 carbon. This is the 1, 2, 3, 4, 5, 6. You need 1 carbon, right? So the only way you can synthesize form a new CC bond so far is acetylide anion alkylation. At 1 carbon, you can use, for example, methyl bromide. And then this is quite simple now, right? You have 5 carbon, 5 carbon. This is just a simple deprotonation. All right. So then you write, so that's your answer should be. Okay. You start from what I'm giving you. First step, sodium amide. Usually performed in NH3 as solvent. Then you get an intermediate. Then you react with so I'm going to say this one more time. I'm drawing ugly because the Apple Pencil situation, okay, not my actual drawing is ugly. Okay, then you get a CC bond formation, right? And then use the H2 Lindlar catalyst. You get what you want. So cis hydrogenation and stop at the alkene. Okay, so this is the perfect answer. All right, so you need to write like this in your exam. Okay, let's do one more. So how do you synthesize 2,6-dimethyl heptane from an alkyne and alkyl bromide? All right, I'll give you 2 minutes. Just take this chance to practice. All right, so we'll definitely have this type of problem in the midterm. So we'll have 3 more to practice on. So take the opportunity. All right. Yeah, this is more complicated. So just think about it. Okay. All right, do you get any idea how to synthesize this? Okay, So apparently, so if I say, oh, you need to start from alkyne and alkyl bromide, basically I'm telling you that you need to form a CC bond with it, right? So that means all those bonds, you need to form a CC bond, new CC bond. So you can then you think about it retrosynthetically. These bond needs to be cut once. Okay, so let's see if we cut this bond. So let me draw an ugly scissor. All right, then okay, you can synthesize it. Okay, let's say if the left part is an alkyne, what do we get? We will get this one carbon, and this would be this one, anion. Plus, if the right one is the alkyl bromide, so we have a 1, 2, 3, 4 carbon alkyl bromide. Okay, so another way is that, so you can, if you do the, if we cut it here, right? So on the right, there is 3 carbon. On the left is 1, 2, 3, 4, 5, 6. 6 carbon alkyne. So it can also be so 1, 2, 3, 4, 5, 6. Okay, plus now the alkyl bromide is 3 carbon. Okay, now we have 2 ways to synthesize this from alkyne and alkyl bromide. But you need to figure out which way is eventually the most is the productive way or the correct way. So on the left, you have alkyl bromide, which is primary. On the right, you have a secondary. Do you remember? So this type of UCC bond formation doesn't work for the secondary alkyl bromide, right? So which means this one is wrong. Okay, so this one is correct. And then you need to write the forward synthesis using this one. Okay, so you start from in this one, you start from alkyne, looks like this, and then deprotonated with sodium amide and reacted with alkyl bromide. All right, so in this one, this is a perfect example to show you that some of even if the retrosynthetic analysis is correct, the forward may be wrong because this CC bond formation cannot happen. All right, so the fourth one, 2 minutes, please. Yeah, you don't need to write the forward synthesis. Just give me, try to give yourself some ideas about how to synthesize this, and you can practice to perfect later. All right, do you get any idea how to synthesize this? So first, compare the starting material and the product. All right, the easiest way to do that. Product 1, 2, 3, 4, 5, 6. C6. Starting material 1, 2, 3, 4. So you need to add 2 carbons, right? 4 plus 2 is 6, right? Do you understand that, right? Okay. And there is only way you can do that, and you are given an alkyne, perfect, right? So the only way is satellite anion. But the problem is a little bit more difficult than the previous ones because you have a ketone. So you need to understand how to synthesize ketone, right? And luckily, there is only one way you have learned so far to make a ketone, which is also from alkyne. Wow, what a coincidence, right? So the way to synthesize ketone is what we call the mercury catalyzed hydration of alkyne. Right? And then to form, you have 2 alkyne that can generate this one, generate this ketone. The first, this alkyne. You can also from this alkyne. Oh. If you count the carbon, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So the difference is that this is a symmetrical alkyne. This is unsymmetrical alkyne. So so the difference between these 2 starting material to get the ketone is what? Do you still remember last week? As I told, synthetically in the chapter, in the slides called the synthetically useful hydration. So for example, for this symmetric, the water can add, the O can add this or add this, but both of them will give this product, right? Because it's 1, 2, 3, 1, 2, 3, and this is 1, 2, 3. This O here, 1, 2, 3. This O here, but in this one, so the O add here is 1, 2, 3. That's correct. But if O add here, it's 1, 2. The ketone should be at the 2 position. So that means if you start from unsymmetrical ketone, the hydration is not synthetically useful because you can get a mixture of product. Okay, so you can, let's see this results in mixture. That means this way is not synthetically useful. So you should start from this. And this is a C6 alkyne, and you have C4. Pretty easy. So you just have a 2 carbon alkyl bromide and acetylide, which can be formed from this. Pretty simple, huh? So in this case is a little bit difficult because you can have 2 types of alkyne, both leading to the ketone. But for the forward synthesis, one alkyne will give a mixture, and thus the ketone won't be formed in as a major product. All right. So only this one will give only 1 ketone. So as a major product. So this one is more synthetically useful, which is the correct one. All right. Let's have it one more. 2 minutes, please. No, if I'm only asking you to devise the synthesis, you don't need to write the mechanism. All right. This one looks a little bit more difficult, right? So, All right, so to solve this one, you need to understand first, let's compare the starting material, all right? So C2, about the product 1, 2, 3, 4, 5, C5. Okay, you need to form a new CC bond, all right? And then we look at the functional groups we got in the product, BR. Is there any way we can introduce BR to a molecule? So you would say it's definitely not BR2, right? BR2 addition, because in BR2 addition, you introduce 2 bromide. Okay, now you only have 1 bromide. So the only way you can introduce 1 bromide at a time is HBr addition, right? So what's the starting material for HBr addition? It's alkenes, right? So okay, so let's see, for a 5 carbon chain, you can have 2 choices for alkene. One is terminal. Okay, 1, 2, 3, 4, 5. The other one is internal. And the condition is HBr. Let's say in organic solvent, usually diazo ether. Okay, then we have a choice to make again. We have a choice to make again. Okay, do we start from the left or the right? Then we think about it forwardly. All right. So from the left, if you add HBr, so and you need to understand the HBr addition is Markov-Nikolov selectivity, right? So the H will add 2 more H. So you have 2 H here. So the H right here, the bromide here. Okay, that's good. The Markov-Nikolov is the major product. How about this one? You have H, 1 H here, 1 H here. So that means if you start from this, use HBr addition, you will get a mixture of product, right? So you can add here or here. So results in mixture. Okay, so that means this one bad. Okay, then we compare the starting material and the intermediate. So 2 carbon, 5 carbon, you need to connect the CT bond. Probably with us. So, but this one is not alkyne. You also need to how is alkene generated from alkyne, right? How is alkene generated from alkyne? It's hydrogenation, right? So if you use the hydrogenation, so you can have starting material should look like this. And for this hydrogenation, it stopped at alkene. So the what you should use is H2 Lindlar, because it's the only catalyst you have learned that can stop at alkene. And then you compare the intermediate and the starting material, 2 carbon, 5 carbon. All right, finally we got this. So we can generate this from 2 carbon unit, which is from starting material, and 1, 2, 3 bromide. Okay, let's start from this. So then 2 and this one. Okay, so this one is complicated because you have a choice to make, which is the you need to understand that HBr addition is Markov-Nikolov selectivity, and thus making this syntax totally unuseful because both have 1 H, so this one won't be generated in major as a major product. Only this one will generate this in major product. Okay, we'll have this one. Okay, so 2 minutes, all right, for this one. Let's answer some questions. Okay, to answer some of your questions, so about what kind of starting material you should use, right? So in the exam, I will clearly state in the problem that how simply the material can be. I usually say you can use any carbon material less than 4 carbons, let's see. And I will give you an example of last year's exam, okay? For the last question, I think if you react this alkyne with the 1,3-dibromo butane, you get 2 more carbons, right? Wait a minute. You can react alkyne with the 2,3-dibromo propane. Yeah, anyway, we can talk about it after class. All right, do you figure this out? All right, so you get this one. The only way you can make epoxide is through epoxidation, right? Using MCPBA, you have learned of oxidation of alkene, right? And then you have alkyne first. So you need to understand that the epoxidation is syn addition. That means that the alkene should look like this. Okay, and this is the oh sorry. This is the cis alkene, all right. And to get cis alkene, what you need to get is the from alkyne, right? CH3, and for a cis reduction, again, Lindemann, very useful hydrogenation because it stopped at the alkene. Okay, then I don't need to talk with you about this. It's quite simple, right? Starting from the two carbons, C2 here, and you get 1, 2, 3, 4, 5, 6, C6. You need to react with 2 carbon units twice, right? We install acyl here and acyl here. All right. So the last one, this is from the last year's exam. All right. So and the problem will be similar. Not always similar. The description of the problem will be similar this year. So I'm asking you to propose a synthetic route what synthesize the following molecule as a major product. All right. You are given only alkenes containing 8 carbons or less as starting material. You need to remember this: 8 carbons or less. You cannot use the 9 carbon, okay, or 10 or 11, whatever, okay. And but you may use any other additional reagents and solvents are needed, okay. You don't need to write the mechanism for the synthesis. You just need to show the reaction conditions. Yeah, that's it. Show the reaction conditions of each step you propose. Okay, I will give you 3 minutes to think about this. And in reality, I would suggest you to finish this question within 5 minutes or 6 minutes in the exam, okay? And so this one is pretty complex. So I will give you 3 minutes to think about, to roughly think about how to synthesize that. Do you think it's difficult? Okay, so the starting material, carbon 8 or less. So how about the product? How many carbon do we have? So this is 6, 7, 8, 9, 10, 16. All right. It seems and apparently, if you look at this molecule, the most important cut of the retrosynthetic analysis should be the CO bond, right? And how many ways you have learned so far to synthesize the CO bond? So you know hydration, right? And if in hydration you add water to a double bond, and we also talked about that you can add alcohol to a double bond, and the selectivity is similar as they add water to a double bond. And you have a Markov-Nikov addition, and you have anti-Markov-Nikov addition, and you have several conditions. You can have acid catalyzed hydration or react with alcohol. You can have mercury, oxymercuration. You can have hydroboration, right? And how about this? So let's cut the left first, okay? So if we start from the alkene on the left, then the alcohol should look like this, right? Another way, if we cut on the right, so the alcohol should look like this. The alkene should look like this. Okay, so on the left, so if you want to add this to here to form this bond, so it's an anti-Markov-Nikov hydration, right? You can understand that, right? Okay, and so for anti-Markov-Nikov hydration, we have a method, but how do you synthesize this? So you can add the water to this, catalyzed by proton, all right? And but what's the problem here? Can you figure out, is there any problem in this route? So if you use proton to add it to here, what you generate carbocation is here. So will this carbocation rearrange? Because it's a secondary, right? So because you have all the bonds here. So if the hydride migrate, the carbocation will generate here. So you can't, right? So you can't. So you cannot synthesize using the proton as the use proton as a catalyst for the for this Markov-Nikov hydration, right? So is there any other Markov-Nikov hydration you have learned? Mercury, right? So you can use mercury to, you can use the oxymercuration. So this is wrong. So how about oxymercuration? Demercuration. So if you use oxymercuration, demercuration, there is no problem for the carbocation rearrange, right? Then you can get this one. And then for this addition, I would say, so there is no problem for the hydride to, and so for this one, this is the anti-Markov-Nikov hydration. No, the reaction with alcohol, right? Because this O will go to this O, and the H will add into here. So this is an anti-Markov-Nikov hydration. And but the thing about anti-Markov-Nikov hydration is that we didn't teach you how to do that. right, with alcohol as solvent. You can do it with hydroboration, oxidation, but eventually after the hydroboration, oxidation, it's water added to the double bond. It's not an alcohol. So basically, the problem of this route, the left route, is that we don't really have any method right now to synthesize this step. Okay, but how about the right one? So how about this one? So you have an alkene and you have a terminal alcohol here. So this is anti-Markov-Nikov selectivity because you add water, right? You have the H on the mole H, OH here. So, and this is hydration. So we have ways to do that. So the ways to do that is that we can use, let's say, BH3, hydroboration, oxidation. Okay, what's the starting material of this? Alkene. Okay, so you have alkene, you do a anti-Markov-Nikov hydration, which add H to here, then you get this alcohol. And how does this alcohol add to here? It's a Markov-Nikov hydration of a Markov-Nikov reaction of alkene with alcohol, right? And then to synthesize this step, you can use a similar method of the mercuration. I'm just going to write the condition here. So in this case, you don't have a carbocation rearrangement problem, right? Because when this reacts with mercury, it will not form. It will form the carbocation stabilized by the mercury. And the OH will add into the more stabilized position, which is the internal position. So to get this one, all right? So basically, this is how you think about this problem. So this is so far the most difficult problem among all we have talked about in the first lecture here. And I would say my problem in the midterm will be of similar difficulty as this one. Okay, maybe a little bit easier, but you really need to figure out all the logic we have just talked about, how to synthesize the complex molecule from using all the reactions you have learned so far. All right, and I think we'll have let's say 5 minutes. Let's say a 5 minutes break, and then we will go to the next lecture, and we will talk about something about the midterm. All right, 5 minutes. I will see you back in 32. Okay, 11:32. right. So I have to let you know that so many of you may feel like overwhelmed when facing this kind of problem. Okay, so how should I start? Okay, okay, so I am at a loss how to do that. All right, so you need to keep in mind that this is the most difficult problem you have encountered so far. So it's not easy in nature, right? And you probably in the final exam you will have like 3 or 4 of these problems in your final exam. You have to solve it. All right, but in midterm there is only one problem of this, and its marks is less than 10% of the whole exam. All right, and how do you know where to cut or where to start with the synthesis? First, so you need to understand just how do we analyze it retrosynthetically. So for example, for this past exam here, all right. So it says that we can start from containing alkenes containing 8 carbons or less, and you can see. So this is quite indicative, right? Because you have 8 carbon on the left, and you have 8 carbon on the right. So this is has already been made easy for you. Okay, and then how do you cut? Okay, so this question is so for you to know how to do a perfect retrosynthetic analysis, you really need to get very familiar with all the reactions you have learned. Okay, and again, this question has been made easier for you because we know the only functional group in this molecule is this oxygen, right? And if you know all the hydration reactions and all the anti-Markov-Nikov, Markov-Nikov selectivities, you would know that to make a CO bond, you have to do a electrophilic addition of alcohol or water to alkene, right? Then it's easier for you to understand that probably we need to cut it on a CO bond here and make this alkene, or we can cut this CO bond here and make this an alkene. And both sides will have 8 carbons, which fits the requirements, okay? And then this problem, the only difficulty of this problem is that you have 2 ways to cut here. One is CO bond here, one is CO bond here. And as we analyze it, so one is not productive because you have a problem with one of the hydration step. All right, so that's the difficulty of this problem. All right, so because you have a choice to make on the left or on the right, not because you have to cut it in the CO bond, because cutting the CO bond, it seems the only choice you have, right? Because you have learned so limited number of reactions, and the hydration or electrophilic addition of alcohol is the only way you can reach the CO bond here, right? Okay, so to finish this chapter, I'm going to give you an introduction of brain chemistry. Basically, nowadays, in reality of research, we not only care about whether we can make the molecule or not, we also care about how we make the molecule. For example, we need to minimize chemical waste, use less toxic reagents or solvents, and we need to use a more catalytic reaction. Basically, you only need to use a catalytic amount of catalyst or reagent to do what you want to do. Okay, so and as a result, if we use less and less chemical waste and less toxic reagents, we will have a sustainable future. All right, so here is a summary for chapter 7. So you need to understand the similarity between the reactivities of alkene and alkynes, and you need to be aware of the issue of double addition, like listed here, HX or X2 addition, and the hydrogenation, addition of water, and the particular case about the alkyne hydration is that it tautomerizes, so you will get ketone as your product. So if you see a ketone as a product, in your midterm exam, there is only way you can make this, right? It's the hydration of alkyne, okay? And then there is also difference of alkene and alkynes, right? Because alkynes can do the CC bond formation. So again, if you see a larger molecule in your as your target molecule in your exam, and you are only allowed to use a smaller starting material, and you only have the choice of alkyne alkylation to make a bigger molecule. All right, so that's simple. All right, and then you need to understand the concept of retrosynthetic analysis and really see if you are given a big molecule, how do you cut it? Okay, and need to have a good grasp of all the reactions. Okay, to increase the chance of figuring out how to make a bigger and target molecule. All right, so after completing chapter 7, you should be able to understand the mechanism of electrophilic addition and radical. Do you still remember which part of this chapter 7 deals with radical? I think most of you don't. I think most of you already forgot. Okay, so the radical part is the anti-hydration. Okay, is the dissolving metal reduction. Okay, then need to apply basic mechanism to rationalize conditions and derive the outcomes of the reaction. Now we have learned alkanes, alkynes. Okay, this is only the start. Think about all the other things you are going to learn in the second half of this semester. Are you afraid now? So yeah, okay, just don't be afraid, all right? So we are going to learn a lot, and Dr. Lee is going to teach you all those others, all right? And again, you are starting to get the ability to apply reaction to the synthesis of target molecules. But so far, we only have all the reactions of alkanes, alkynes. So that's the easy part of it, right? Because you only know these kind of reactions. So we won't test you beyond the scope of these reactions. But think about it. In the final exam, you have like 10 classes of reactions of all these compounds, and you are given a molecule to synthesize. That's very terrifying, all right? But don't be afraid, it's fun, all right? So, all right, let's talk about the midterm. So let's see, where is it? So the midterm will be this is wrong. So the midterm will be held this Friday from 11:30 a.m. Okay, it's an open book. Did you see that? Okay. Can you see this PDF now? So the midterm will start at 11:30 a.m. All right, this is an open book test, meaning that you can okay, so you can use a lot of things. So you can use all the notes, your own study notes, and the textbook, but no other sources. Okay, so you cannot go to internet and search for answers, and you cannot use molecular models. Okay, and no calculators, or you cannot have a guy next to you helping. All right, this is not permitted. All right, so I think around the 70 of you have already registered for the test. That means around 30 of you haven't done so. So you have to register for the test to be able to join the test and get your test marked by October 7th, right? So that's tomorrow night, okay? Tomorrow night, 12 a.m., all right? So you have to register by then, okay? Otherwise, you won't be able to take the exam, and you will lose 15% of your grade this semester, right? And after you registered, you will get a password to join the test on Friday. So open book test, as I said, and you need to use a dark pencil or pens because this is Zoom test. So you need to write on your own paper, and because the papers will be submitted online, so just make sure your writing is really dark enough for us to see online, or for us to print it out and clearly see your answers, okay? And so on each paper of your exam, you write on it. So you should have your name and student number on the top right corner, okay? This is essential for us to recognize which paper belongs to whom, okay? And so you can prepare these pages for yourself ahead of time. For example, so on Friday before 11:30 p.m., you can have like 10 A4 papers, right? And then you have each paper have your name and the student number on the top right. That really save you a lot of time. So if you try to do it during the exam, you are losing time, okay? And the test time is 1 hour, all right? So you will have to have Zoom camera, speaker, and open microphone. Okay, all three are essential. So we will have invigilators or those monitors open, like we have tutors like monitoring the exam. Okay, we have to see your camera, we have to see you open your speaker, and you cannot wear any earphone. Okay, open microphone. All right, these three are essential for us to know that you are not cheating on that. All right, and so your camera should be showing you at work. So do not put your camera facing your answer sheet, okay? Because if you place your camera to your answer sheet, all the other guys, all the other students can see your answers, okay? Because it's a Zoom section. And don't worry about your privacy, these images will be deleted. And actually using a device such as a smartphone is quite good for this purpose, because the smartphone has your camera, speaker, and an open microphone, right? So you can just put your camera, put your smartphone ahead of you, in the front of you, right? So that will be perfect. Okay, so you may choose a display background for privacy. It's fine. No earphones, just like that. All right, just prepare it early. Okay, don't wait until like 11:30 to start to test your camera, speaker, open microphone. Okay, so on Friday, so the tutor and I and all the monitors will be start the meeting at least 30 minutes before 11:30. Okay, so we will be there, so you can join anytime you want. Okay. Oh, you don't need to test it now. Okay. Okay. So in addition, you may also want to have another device to access to Moodle or email, because at the start time, I will email you a PDF of the exam. All right, and then you can open it and start to answer. Okay. So it's best if you can work in a quiet room by yourself without disturbance. I know some of you may have some problems getting to a quiet place. So I know the school library has some discussion rooms and private study rooms. So you can reserve that. And really, you being in a quiet room by yourself is quite good for taking the exam. Okay. So during the test, okay, before 11:30 a.m., you should log into Zoom session and have your camera, speaker, open microphone on. Okay, for the duration of the test, and to show your face. Okay, don't show your answer. All right. So the test question paper will be sent on Moodle News and announcement, which you will get it from email as well. And you're given 60 minutes to write your solutions. All right. So if I give you any time extensions, I will be announced to you through the Zoom. Okay. I will have a broadcast, and I will let you know by talk to all of you in Zoom. Okay. So if you have questions about test, use the private chat function to talk to me. And when the end of test is announced, you should stop writing. All right. So there is an invigilator and me and tutor monitoring you in several break rooms. Okay. So after I announce that, okay, the test is finished, you should stop writing. Okay. I don't want to see any of you writing. So that's cheating. Okay. And so if you cannot open Zoom, or if you cannot communicate with me in Zoom, I will be monitoring my email box too. So you can send an email to me to communicate. All right. So another important part, submission after the test, right? You need to submit 2 things. Keep in mind 2 things, all right? So you should, with your camera and the Zoom still on, the visible of your face, you should submit your solution pages, okay? So if you want all the questions, all the solution pages to be marked, you should submit all the pages of your solution pages within 30 minutes after the end of test. So let's say if the test is finished at 12:30, so I will set the deadline, cutoff line on Moodle of the submission link at 1 p.m. All right, 30 minutes after the end of test. Okay, and if you are submitting photos, make sure they are of high resolution for easier for us to mark and to give every credit you deserve. All right, and upload your answers in order of questions. And if after you have uploaded your solution by Moodle, then you can log off and end your Zoom section. Okay, so keep that in mind. When you are submitting your answering sheet, do not turn off your Zoom. We want to see your face when you are submitting your answers. Okay, and then second, you must not discuss the test with each other until after it is announced on Moodle News and announcements. Okay, so after we have make sure every answering sheet is collected and they are in order, and I will announce on Moodle that, okay, I have collected all the midterm papers, then you can discuss it with each other, with your friend, okay? And then the second thing you need to upload, and the deadline for the second upload is within 1 hour of the end of the test, okay? So if we stop the test at 12:30 on Friday, you have until 1 p.m. to upload your answer. And you have 1 hour, which is until 1:30 p.m. to upload an identification file. Okay, what does that mean? So this is in the purpose of like let us know the guy taking the exam is truly you and yourself. Okay, so you need to give us a selfie of high resolution showing yourself from your shoulder upward, holding your student card and the first page of your solution. All right, so so for example, so if this is my first sheet of my answering, and I need to take a selfie like this, all right, like this, all right. Make sure it's a high resolution. All right. So we need to see the photo of your ID card and your face. All right. And keep the hard copy of your answer sheet and the soft copy, okay, of your answer sheet, both. Right. Save one copy on your computer. The copy that you have uploaded, save a copy of that, and also save your physical answer, the paper. Okay. We may need it later. All right. So I think this is not the first time you have experienced a Zoom lecture, right? Okay, let me answer some questions. Okay, so the authorized sources does not have to be in hard copies. That means you can use your iPad to check your notes. It's fine, but you are agreed. You will be agreed. Okay, you will agree to not go to internet for help. Okay, so that's cheating. All right, so you can use your iPad, electronic copy of your notes. It's fine. Okay, is the registration of midterm on Moodle? Yes, you can find it in the news and announcement page of the Moodle. There is a link, or I have already sent to your the Moodle email account, the email address you listed on Moodle of this link. Okay, so you can go to this link and register. Okay, just be sure to register. So there is no forgiving. Okay, so if you pass the deadline of registration, you lose 15% of your grade. Okay, and on Friday, if you pass the deadline for the submission of your answer sheet, or you pass the deadline of the submission of your identification file, okay, you lose 15%. All right, don't make that mistake. It's okay, 15% is a lot. Okay, so from now to the exam, you can send any questions you have to me or the tutor, so we can answer you as in detail as much as possible to help you really prepare for the exam. And if you have any technical issue, okay, so just let us know. Okay, we will have a brief review of the first half of the semester. So I won't talk about a lot about the LCAM part because we just learned that. Okay, you don't need to review something you just learned. Okay, and okay, so the principle of the exam, the content of the exam is that everything taught at class will be covered. So if it's in the textbook and we didn't teach it in the class, okay, they are not required, but you are welcome to learn it. And if during the class I said, okay, this is too hard for you, this is beyond the scope of the exam, okay, it won't be tested. All right. So the good thing about the Zoom section is that you can always review my videos on the YouTube, so you can see, okay, I have evidence. You said that won't be covered in the exam, so okay, I will keep that promise. Anything I said, this is beyond the scope of this class, it won't be tested. All right. So chapter 1, 2, 3, we were dealing with some basic concepts and do some review, and so you need to know how to derive correct IUPAC names. Okay, so you should by now have watched all the small videos by Professor Chu, and you should do that. And you should be able to draw Newman projections, and you should be able to calculate all the energy if I give you enough data to do so. And you need to understand all these strings. Okay, torsional, angular is also called the angle string. Okay, and the steric string. And you need to be able to draw chair conformations of any cyclohexane. Okay, anything, any cyclohexane. Okay, and identify, draw the axial, equatorial, understand ring flip. Ring flip is important. Okay, and analyze the relative stability of the two chair conformations. Okay, so very So a very important concept is that the single bond can rotate. All right. So I have talked about this. So if I give you a product, ask you to write the starch material, okay, the product may not be seen like anti-addition, then you need to rotate it, make it look like anti-addition. Then it's easier for you to see the starch material. Okay. Newman projections. Remember these rules, how to draw Newman projections. Okay. This is dot from carbon, circle back carbon, 3H, 3H. Okay. Then you have a staggered conformation, so 60-degree dihedral angle each away, and you have eclipse, which is 0 dihedral angle here, right, and the 120 degrees away from each other here. All right, there are a lot of conformers in between. But if I ask you to draw a Newman projection, I will be clearly saying that, okay, you need to draw like all three eclipsed conformation, or I will say, or draw all three staggered conformation. Okay, I will be very clear about that. And based on the staggered conformation, you have eclipsed conformation you have drawn. And if I give you some energy cost data, you need to calculate all of these data, right? So if 2-methyl, 3.8 kilojoule per mole, it's Gauss. So methyl Gauss, okay? Methyl eclipse, okay? Methyl eclipse, 11. And so this has 0 kilojoules, so this is the most stable conformation, right? And this is 19, this is the least stable conformation. Okay, and for the chair conformations, you need to understand we have axial, ring equator, and all these informations. Okay, what's the answer? What's the question here? I will upload today's recording right after the lecture. I know. Okay. Okay. So we have top face, bottom face, ring flip. Very important concept. Okay, carbon 6 goes to here, carbon 3 goes to here, and all these changes you need to understand. The equatorial become axial. All right, but what doesn't change is that H used to be pointing up, keeps pointing up, because but if it's equatorial, it becomes axial. Okay, so it's for this one, equatorial pointing down, axial pointing down, still pointing down, different in equatorial and axial position. And we also learned the 1,3 diaxial interactions. And you can see the larger the functional group, the interaction between 1, 3, these two substituents become larger. All right, so this is a question of last year. So basically, this is from Professor Chu's test. So you have, she gave you cyclohexane, ask you to draw 2 chair conformation, okay? And you need to draw 2. And he asks you, are the 2 chair conformers of the same stability or not? Apparently not, right? So if not, which one is less stable? So this one is less stable. Why? Because there are a lot of 1,3 diaxial. So this isopropyl with these 2 H, this OR with this H, this methyl with this OR and this H, okay? And these are all in equatorial position. So this is more straight, all right? And for chapter 4, there is any questions? Let's see. Okay. No. Okay. So chapter 4 deals with stereochemistry. You need to recognize and understand the implication of chiralities. Okay. And you need to assign the configuration of R and S. So this, you probably have a lot of difficulties completing the stereochemistry drill, right? So this will be on exam, totally. Some of them, a lot of them, yes. So about like 10% of your score will be assigning the R and S. And that's the easy one, right? That's easier than the synthesizing target molecule problem. Okay, so and now you know how to name, how to get R and S. Then you need to come up with complete IUPAC names. So the IUPAC names, the complete IUPAC names should have these R and S specification in it. Okay, don't forget it. Okay, you need to draw enantiomers, diastomers, and perspective drawings of facial projections. Facial projections is important. Plane of symmetry, because if you can find the plane of symmetry, it's not chiral. And stereocentrics, a carbon with an or atom with 4 different substituents. 2 very important concepts. Okay, and chiral-chiral interaction and chiral-achiral interactions. Okay, just remember If it's 8-chiral slippers, both of your feet feel comfortable. But if it's chiral-chiral interaction, so it gives different energy. If you missed it, you will feel not uncomfortable. Right, facial projections. All right, so remember that if I give you a facial projection like this, so by definition, C and D are pointing to you, okay, facing you like this. A and B on vertical position are pointing to the back like this, okay? So it's by definition. So if you see this facial projection, imagine this, right? And then facial projection are really good for multiple and consecutive stereocenters. For example, 1, 2, 3, 4, 5, 6, 6 carbon, 4 of them are chiral. So if I ask you to assign these 4 stereocenters, R or S, you should be able to do it very quick. All right, don't waste time on this. Okay, and the Carr-Engel-Krylov convention, just assigning ROS, right? And the smallest in the back facing looks through this direction, and from the biggest to the smallest, if it's counterclockwise, then it's S. If it's clockwise, it's R. All right, and see here. So complete IUPAC name of this, you need to put an S here. S, bromochloroiodine methane. Right, and remember these extended comparison is important because it's not gonna be as simple as this, like 3 atoms. Okay, so you are going to facing quite complex substituents like this. Okay, you need to compare one by one. Yeah, I think most of you already understand that. So double bond kind of counted as 2O, triple bond counted as 3C. Triple bond C, it's CCC. Okay. Okay, the concept of diastereomers. Okay, 2R, 3R, and 2S, 3S are enantiomers, and 2R, 3R, 2R, 3S, 2S, 3R, they are diastereomers. Okay, so simple way, if R in the middle is S, R in the middle is S, diastereomers. That's enantiomers. Okay. So, and the concept of meso compound. So a lot of you are still confused about that. So I'm going to summarize it here. To judge if one compound is meso or not, so a meso compound must have 2 or more stereocenters. Okay, the first thing to look if it has 2 or more stereocenters. If it does, go to the next phase. That means if it does have 2 or more stereocenters, it should have a plane of symmetry to be qualified as a meso compound. Okay, so many of you have difficulty finding stereocenters because some may look like stereocenters, but it's not because 2 substituents are the same. Okay, then after you find the stereocenters, some of you may have difficulties in finding the plane of symmetry. Okay, so practice. There are like 50 problems on the stereochemistry drill, so you can try as much as you want. Okay, so 2 steps. 1, 2 or more stereocenters. 2nd, plane of symmetry. And that's a review of isomerism. So we have constitutional isomers and stereoisomers. And stereoisomers have enantiomers or diastereomers. Okay, keep it easy in mind. So 5 to 6 is the biggest chapter of the first half of the semester, and deal with alkene and especially electrophilic condition and all these reactivities of alkenes. So using the CIP rules, you should be able to judge whether it's Z alkene or E alkene. And again, if you have an alkene in your naming that has E or Z, you need to write E or Z in the beginning. Okay. If it's a terminal alkene, all right, with no easy issue, then you can you won't need to write E or Z. Okay. But if there is easy, you need to write it easy in the beginning. Just as I said, when asked for full IUPAC name in exam, stereochemistry is required. And also the same extension of rule applies here. And the drawing a mechanism is important. There will be definitely a question about asking you to draw a mechanism in the exam. Okay, just don't draw a. I think we have practiced this several times in the class. So there are some rules curve the arrow indicate the electron flow. So you should start with a lone pair or negative. You cannot start from an atom, something like that. You remember that. And we talked about reaction coordinate diagrams. Okay, so you will need to know, okay, this is the starting material, this is the product, this is the transition state. All right, any questions? Let's see. So a compound that has plane of symmetry, but with less than 2 stereo centers, that means it's achiral. Okay, so if you have a compound only have one stereo center, and it has a so the first requirement for meso compound is that it has to have 2 or more stereo centers. Okay, and does have then you judge whether it has a plane of symmetry. So if a molecule doesn't have a 2 or more stereo centers, but it has a plane of symmetry, it is achiral. Okay, it's not chiral. All right. So meso is also achiral, but it's the special achiral. Okay, so yeah, that's that. Okay, so you need to understand, for example, if I give you a multi-step reaction coordinate diagram, you need to understand, oh, there is a intermediate, so starting material, product, intermediate to transition state. Okay, and the rate determining step is here, because it's the highest energy transition state. So the rate determining step is the step containing this from this to this. Okay, and yeah, and so we also have did I talk about this? Okay, we talked about it. Okay, so we also have extending to why Markov-Nikov's rules is happening. So the result of the Markov-Nikov's rule is that the H at 2 mole H, okay, major regional isomers, and the H at 2 mole H, major regional isomers. Okay, the reason behind that is that there is a carbocation intermediate involved, and you need to know that tertiary carbocation is the most stable, and the methyl carbocation is the least stable. And also a thing you need to keep in mind is the Hammond postulate. So an endergonic reactions, which means the product is higher in energy than the starting material, the transition state will look like the product. But if it's an exergonic reactions, if the product is more stable than the starting material, then the transition state will look like the starting material. All right, and this is the logic chain for why Markov-Nikov product is generated, right? Because we have a more stable carbocation, and because transition states looks like carbocation, so we have a more stable transition state. And the more stable transition state means faster step 1 of addition. And because the overall rate is determined by step 1, so the faster overall electrophilic addition. And because the faster overall addition, Markov-Nikov product is preferred. All right, be aware of this chart. And we also talk about since the carbocation is intermediate, how do we know it's carbocation? Because carbocation has a characteristic rearrangement reaction. So you can from a less stable primary carbocation, you can rearrange to tertiary carbocation, which is more stable. For example, this 4-membrane can rearrange to 5-membrane, all right, because secondary carbocation is more stable. And yes. Okay, then we have a halogen addition, which is a stereospecific addition. Okay, it gives anti. What is stereospecific? It's a reaction convert one isomer of starting material to one isomeric product. So this is also something very difficult. Some of you have asked me about this. So stereospecific reactions, to determine whether a reaction is stereospecific, you can't get it from one single reactions. The correct way to do this is that you see 2 reactions. So these starting material of these 2 reactions are stereoisomers. For example, cis and trans. Okay, then see the products of these 2 reactions. Okay, the first product is 2s, 2s3s, 2r3r. The second one is a meso.
So these two and this one are stereoisomers. Okay, the starting material are stereoisomers, and under the same reaction conditions, it gives products that are stereoisomers. Okay, so stereoisomers. So that is the definition for the stereospecific reactions. Okay, then you can see addition of halogen to stereospecific. Okay, so regioselective reactions, you can judge from one reaction, more B and form than C. B and C are constitutional isomers. And the stereoselective reaction, more B and form than C. B and C are stereoisomers, like enantiomers or diastereomers. Okay, stereospecific reactions, you cannot judge it from one single reaction. You have to have two reactions. And the starting material of two reactions must be stereoisomers. And if the product of two reactions are stereoisomers also, then you can say it's stereospecific reactions. Okay. And then we can see if we use water as solvent, it will form a halohydrin instead of the dibromo addition. Okay, and the halohydrin formation, you can see the unsymmetric alkene is different mechanism. So this is stabilized carbocation. So the O will form at a more congested position. Okay, and then we talk about hydration. For the normal hydration, we need to use water. You use water and strong acid as catalyst, and because it's also following the Markov-Neifeld rule, and so in comparison, so if you use alcohol as the solvent, we can have the alcohol addition to the double bond. As you see here, right? So you form an ether, just like a Professor Chu's midterm last year. So she gave you a product that has the CO bond two sides. So that means that if you see this product that is given to you, you need to think about, okay, it comes from the acid catalyzed Markov-Nikov addition of alcohol to alkenes. Then, but the Markov-Nikov acid catalyzed hydration or addition of alcohol has a problem because carbocation can rearrange. So these are two methods that the carbocation does not form carbocation, so does not rearrange. Okay, oxymercuration, demercuration is one of them, and no carbocation rearrangement are observed. And this is following the Markov-Nikov rule. Okay, so step 1 and 2, oxymercuration of this one, and the water adds to the more congested position here. And second is the demercuration. Demercuration is not stereoselective, both. So if this is pointing down, both pointing up, pointing down, H will be generated. But for regioselectivity, it's Markov-Nikov, but it's non-stereoselective. All right, and so this is a comparison between two types of addition. So for unsymmetric alkenes, so for the halide like dihalogen or mercury, so it will form stabilized carbocation, no rearrangement, nucleophile attack at the more congested position. So if you react with proton, and it's non-stereoselective because the nucleophile can react in the top or in the bottom, and if you have a possibility of the rearrange, so it will rearrange. So when you propose a reaction to give the target molecule in the exam, keep that in mind. If you propose a carbocation-based electrophilic addition, it will rearrange. And if it's rearranged, so it's your product will be not getting as the major product. All right. So if you are, let's say, if you are asked to draw a synthetic route towards a complex molecule, so you just for each step you just need to draw the starting material and the product, okay? And you don't need to draw the intermediate. For example, you don't need to draw this or this in your answer to synthesize the target molecule, okay? But if I ask you in other questions to draw a mechanism of a reaction given, you need to draw you need to draw this because this is part of the mechanism. So you don't need to draw mechanism when you are devising a synthetic route, but you too need to draw all these intermediate and arrow pushing when you are asked to draw a mechanism. Okay. And okay, another non-rearranged the method is hydroboration oxidation. So it gives you but keep in mind hydroboration oxidation can only do hydration. So you cannot add alcohol. You are not learning. You haven't learned that, so you cannot use that. So it's just the hydration, no alcohol addition. Okay, and the hydration follows anti-Markov addition because of this boring is too big. It will clash with the methyl. So the H will goes to less H. And the sterol addition is the stereochemistry is syn. All right. So the B and the H can add to syn. So that means the OH, the CB bond will be replaced by CO bond, right? The CO bond and the H are syn. Okay. And so hydration without rearrangement, two types. One is mercuration and demercuration. The other one, hydroboration and oxidation. All right. Be familiar with all those stereochemistry and radiochemistry. Okay. Hydration. Okay. We can use the platinum, palladium on carbon. We can do the hydration of alkene. Right. And we can do oxidation of alkenes. For example, we can do the dihydroxylation, which is syn addition. This is the mechanism, a little bit complex. Okay, we can also do the epoxidation. So if I give you epoxide, this is the only way you can make it. You have learned so far. All right. So MCPBA reacts with alkene, syn addition. It's only possible for syn. All right, because it's a string membrane. It's okay. Then on the analysis. So the mechanism of on the analysis is quite complex. But you need to keep in mind, a simple way to remember this is that CC double bond breaks, okay? Each C is now connected to O in double bond, okay? This C, double bond O. This C, double bond O. This carbon, double bond O, ketone. This carbon, double bond O, okay? So for for this compound, you have two products. For this one, also two. For this one, because this is linked, all right? Carbon double bond is broken. Each carbon now connect to a double bond O. Okay, so reactions of alkynes. You have these reactions with alkyne. Okay, let me answer your question first. Okay, it's two there. Okay, never mind. Okay, so the alkyne addition, electrophilic addition, can add twice, right? Generate this one. All right. Okay, so for the halogen, it's also the same. You can add once, generate a trans, add twice. Tetrahalogenation. All right. And alkynes to cis alkenes, H2 Lindlar stopped at alkene and the syn and cis alkene generated. All right. And then if you use normal hydrogenation, use palladium on carbon, it cannot stop at the alkene. It will only stop at the alkanes. Keep that in mind in synthesis. Okay, this dissolving metal reduction give trans. Mechanism is different. And so you can control the amount of reagent. So if I say I give you one equivalent of CrCl2, you write this product. If I give, I say, oh, I give you two or more equivalents of chlorine, then the product is this. Keep that in mind, all right? And for the hydrogenation, you can control the geometry of the alkene by using different method. And if you can prevent the over reduction by using Lindlar catalyst, it stopped at alkene. All right, and then we can do the hydration, but remember the ketone is final product. If you see the target molecule has a ketone in it, it has to come from the hydration of the alkyne. Okay, keep that in mind. All right, you can also do hydroboration, the same as the alkene, but again, it stopped at a ketone. Okay, so this one will change very quickly to ketone. And that's the mechanism for ketone tautomerization, the basic condition. Remember, there's another mechanism under acidic conditions. Okay, they are different. Okay, then for example, and to summarize, compare them with all these control of amount of reagents to give different products. You can see the addition of water. You do not need to control it because it doesn't add twice. And once this is generated, it won't. The double bond will be gone to give this ketone. Okay, it won't happen twice, the hydration. All right, so that's so this semester is my first competition. So I guess if we are doing it face to face, it will be more interesting. But nevertheless, it's interesting enough. So after the midterm this Friday, you will have a reading week, okay? And then relax. Then after you come back from the reading week, Professor Lee will take over. And so Professor Lee will be in charge of the second midterm and half of the final. So you will still see me in your final exam, okay? I will be in charge of half of the final exam problems. So you will see me there, okay? And then, so even another thing is that even after today, in the second half of the semester, so or in the second semester, I have my consultation hours still on Friday. So if you prefer to ask me some questions, no matter it's other class or this organic chemistry or research, something like that, you can always knock on my door every Friday, 2 to 6, HOC 102. Just welcome to come by, okay? So, so let me say this. So organic chemistry is very important to me because my undergraduate advisor teaches my introductory organic chemistry. And then I think, okay, organic chemistry is pretty interesting. So I joined his research group. So he became my undergraduate advisor, okay? And so I would say organic chemistry really changed my life. So I start from, like you guys, don't know anything about the chair conformation, okay? And 10 years later, I'm teaching you chair conformation, okay? And so when I was in Peking University, so as an undergrad, at that time, Professor Lee, so Professor Lee Xiaoyu is still a professor there. So I was his student, okay? I was Professor Lee's student when I was undergrad. Now we are sharing this class together. So organic chemistry is really, really important for my life. So if any of you eventually end up taking organic chemistry as your career or do research in organic chemistry, even if there is only one of you, I will feel very happy, all right? Maybe it's not in my group, in Professor Chu's group or other groups. So from 10 years experience, organic chemistry is really fun and it has changed my life. So if I can change a little bit of your life, make you happier or make you like organic chemistry more, so I would say I've reached my goal for teaching, okay? So even after today, and you can still come by anytime to my, not anytime, Friday, please, okay? Friday, 2 to 4, and ask me any questions, all right, about research or class. So with this, I would like to thank you for your attention in the first half of the semester and wish you good luck in your midterm, okay? Do well, all right? And if we have chance, we can see each other. Although I barely see you, all right? You may recognize me on campus, but I can't, all right? All right, see you on Friday. So